everybody, and welcome to our last video for Unit 3, which we're going to talk about solutions. And this is going to be a relatively easy topic because, first of all, we talked about this in Chem 2 already, and there's not anything really too complex to know so far about solutions in this particular unit. So, when we talk about solutions, another way to say a solution is that solutions are also known as homogeneous mixtures. Homogeneous mixtures. And that's because they're called homogeneous mixtures. They are uniform in their properties through a given sample. So this means that their macroscopic properties do not vary. Can't talk today. So their macroscopic properties do not vary. And macroscopic just means what can be seen, I should say seen, with the eye. So if I have a solution or a true homogeneous mixture, and if there's some stuff in there, some liquid, let's say I have a saltwater solution, a sugar solution, ultimately it doesn't matter. But if my solvent is water, a true solution would have those particles evenly distributed throughout the entire material. And I wouldn't be able to see the different particles. I can't differentiate the solute particles, which would be the salt or the sugar or whatever, from the solvent particles. So that's what we mean when it's uniform in composition or uniform in their properties. And of course, there's a lot of different types of solutions that we can have, and it's not always just a solid solute dissolved in water. But air, for example, is a solution, and that's because I have a homogeneous mixture of gases. So I have nitrogen gas and oxygen gas and CO2 and H2O and little bits of argon in there. And they are evenly distributed. When you take a breath, every breath should have the same exact concentration of all of those molecules, and that's because they're equally distributed. Carbonated water, so if you buy a seltzer right before you open it up, all of that carbon dioxide gas is evenly distributed in the liquid water. Ethanol in water is another example, not something you might be as familiar with seeing, but in that case, that is a liquid solution of two completely miscible liquids, and miscible just means that they mix freely. It's a word that we use instead of saying like, oh, ethanol dissolves in water or they mix together. When we're dealing with two liquids, we say that they are miscible in one another. Brine is another example of a liquid solution. So in this case, however, you have a solid solute that's dissolved in a liquid, in this case, water. So great example of brine would be like what you would use to make pickles or something. Dental filling alloy and a gold silver alloy. So both of these are actually solid solutions. And that last one is an alloy of two metals. So in this case, gold and silver might have pretty similar atomic radii. They're right above each other on the periodic table. They might make a substitutional alloy because those radii are very close in size. However, for the one above it, the dental filling alloy, liquid mercury and solid silver, right? These ones, we're not going to necessarily make the same kind of alloy because this is a liquid, but we do have some tiny little bits of liquid mercury that are dissolved within a solid solvent. In this case, our solvent is the silver. I don't think they really make dental filling alloys with mercury anymore because, as we know now, mercury is very bad for our health. But yeah, so we don't have just solutions or homogeneous mixtures of just, Kool-Aid or lemonade. There are tons of different homogeneous mixtures. In fact, many things that you're familiar with are homogeneous mixtures where we can't see the different particles that comprise them. So, how do we represent the concentration of a solution? One way that the concentration of a solution can be expressed is in units of molarity. Molarity. So you might hear me say, all right, grab the 3 molar solution. That particular value tells us the concentration, how many moles of solute are dissolved per liter of solution. And that's always denoted by this concentration value, which we call molarity. Molarity is always expressed as a capital letter M. I have always underlined it. That's what my professors did for me, and that's just how I've always done it. Sometimes you might just see a capital M with no line. Ultimately, it doesn't matter, but it does have to be a capital letter M. So this means, let's say for a lab, you were asked to grab some 3 molar hydrochloric acid. That means that you would have dissolved 3 moles of hydrochloric acid per 1 liter of solution. Okay, so it's the number of moles per liter of solution. So if I take a look at these 2 images down here, this one on the left right here is a very dilute concentration. There's not a lot of stuff that's in here. There's not many moles of solute particles that are in this particular solvent. However, here, this particular solution would be pretty concentrated because it has more solute particles that are dissolved per liter. So if we were to imagine that whatever this volume is 1 liter, and if this is also 1 liter, this one right here would have more moles of solute that's dissolved in it, whereas this guy has less moles of solute. Pretty straightforward. We call something dilute or concentrated. Depends on its concentration. There really is no cutoff for what's low and what's high. It kind of just depends. Usually when I say something is concentrated, usually means like the top concentration that it comes as, but ultimately dilute usually I would say means like 1 or below, whereas concentrated might be a little bit higher than that. Let's try this one right here. So a solution is prepared by mixing 1 gram of ethanol with 100 grams of water to give a final volume of 101 milliliters. Calculate the molarity of the solution. So we do have to identify what's dissolving in what. So it looks like here ethanol is my solute, and the solute is what is getting dissolved. Whereas my solvent is typically in greater quantity, whatever is doing the dissolving. A lot of times it's going to be water. So I want to know how many moles of my solute are dissolving. So I do have to convert 1 gram of ethanol to moles of ethanol. So 1 mole of C2H5OH over 46.08 grams of ethanol. You solve for that, and you should have 0.0217 moles of ethanol. So that's the top part of my equation, right? So molarity is what I'm trying to find is equal to how many moles of solute are in liters of solution, the whole solution. So we want to know, what is the volume of this whole entire system? We know already that this right here has a volume of 101 milliliters, right? So this is going to be the volume of the solution. However, we need to make sure that we convert this to units of liters. So I'm going to put liters of solution down below just by moving that decimal place over 3 times. And when you divide, you should get a final answer of 0.215, and we say this unit as molar. Molar. So I would say this produces a 0.215 molar solution. Very straightforward. Of course, you might have some different types of problems where you would solve it a little bit differently, but overall, molarity is always moles of solute per liter of solution. Another very important technique in chemistry is you need to understand how to make a less concentrated solution from a more concentrated solution. And I do this all of the time. I always use this equation because I tend to buy the very concentrated materials, and then I just dilute it to whatever concentration I need for a particular lab. A very relevant equation. So sometimes you may need a different concentration of a solution than you are provided with. In that case, you must perform a dilution. This is done by adding solvent to the solution. And our equation kind of looks like Boyle's law, right? So M1 over M1 V1 equals M2 over V2. So the concentration of 1 times the volume of whatever concentration I need is equal to the molarity of the second one and how much of that. So what does this mean, right? Let's say I wanted to make 1 liter of a 0.2 molar solution, okay? So I want 1 liter of a 0.2 molar solution for a lab. And I only have 6 molar hydrochloric acid. I would need to figure out what volume of that 6 molar hydrochloric acid do I need to make 1 liter of a 0.2 molar solution. That's what this particular equation is telling us. So of course, because these are next to one another, these variables, the higher the molarity, the lower the volume. Okay, so the higher the molarity means less of that. When I dilute that to decrease the concentration, I would have to add more solvent to do that. So here's a great example. You are asked to make 250 milliliters of 1.5 molar hydrochloric acid from a stock solution with a concentration of 12 molar. How many milliliters of the stock solution do you need to make the diluted solution? So we want 250 milliliters of a 1.5 molar solution. And we want to know what volume of this 12 molar solution do I need to make this, okay? So basically you would solve this like you would any algebra problem, and you find 31 milliliters. It doesn't matter what units of volume what units your volume is in, because whatever unit is on this side of the equation would be the units that you get on the opposite side of the equation. So I could just use milliliters, you can use liters, you might be given centimeters cubed, doesn't matter. Whatever unit of volume is on one side, that's the unit of volume that is on the other side as well. So then it explains, how would you make this solution, right? So, all right, I have the answer to this. Well, how would I do this? And you're going to do a lab where you are actually going to go ahead and make some solutions. But what I would do at this point is, and I'm going to get a text box here. Let's actually, do I need a text box? I don't think I do. Let's just, there we go. We don't even need a text box, Mrs. Snyder. What the heck were you doing that whole time? Okay, so we would measure out 31 milliliters of the 12 molar HCl. Like I said, I like to underline my things because I know for a fact that that's molarity. So I would measure that out. And it doesn't matter how you would measure it out. You could say using a graduated cylinder. You could say, or a graduated pipette, whatever you want, right? Probably a graduated cylinder would be best for this. Period. So you measure that out. The best way to make a solution is using a volumetric flask. So we would add this volume of HCl to a volumetric flask. And a volumetric flask looks like this. Let me try my best to draw one right here. Kind of looks like it's got a very narrow top. Okay, can I draw on there? I don't think I can. Okay, so it's got a very narrow top. It comes down like this. And it's got this big bottom. You might have seen them floating around in this lab before. And there's usually a line right here. So let's say this is a 250 milliliter graduated cylinder. We would measure out the 31 mils of the 12 molar using a graduated cylinder or a pipette, and we would add this to the volumetric flask. So you have your hydrochloric acid sitting there at the bottom. So what do I do next, right? Then we would add water until the solution has a total volume of 250 milliliters, which would be up to the line on the neck of the flask. So then I would fill it up to 250 milliliters. So I'm not adding 250 milliliters of water. I'm just adding it up to the line. Now, sometimes, right, when you add this, then we want to mix it, right? So I'm actually going to add to this. I'm going to say invert the flask a few times to, on the next line, to thoroughly mix. You might see, because of intermolecular forces, hydrochloric acid and water like one another, so they will hydrogen bond. So let's say you added the 250 milliliters of water and it was right on the line. You inverted the flask a few times after you capped it. So we'll add right here, cap the flask, and invert a few times. That's important to put a cap on it. And you might see that after you mix it, the volume actually goes below 250 milliliters, not by much, but it will go down a little bit. If necessary, if that happens, add more water until the volume is back up to 250 milliliters. So sometimes we might say, and this is okay too, you could add water before you add the hydrochloric acid as well. And that's probably actually a better technique because you never want to add acid to water, and especially a strong acid to water like that or a very concentrated one. And that's because it can gain a lot of energy very fast, because when the hydrochloric acid starts to dissociate, it releases a lot of energy. We're going to talk about that in another unit. So actually we might want to add a little bit of water first. So add this volume of HCl to a volumetric flask filled, or we'll say partially filled with some distilled water. Just a better practice, I think, and you're going to get some practice with this in class, so no worries. I got a nice lab for us to practice dilutions and making solutions and error analysis and spectrophotometry, which is interesting. As always, if you have any questions, let me know. We do talk about this in Chem 2, so most of you have seen this before. But as always, if something arises, please let me know. I will see you in Unit 4 at this point, which is all about chemical reactions. I'll see you then. Bye.